Hello, my amazing AP Chemers. We're going to start chapters 11 and 12 today. So chapters 11 and 12 talk about solids and liquids, and which are condensed states of matter, since we've already talked about gases. And the main difference between gases and the condensed states is the presence or the significance of intermolecular forces. So this chapter basically deals mostly with intermolecular forces. As always, we have our learning objectives here that you want to read before your test. And let's start our notes with a brief overview, kind of a reminder of the difference between solids, liquids, and gases. So we have particle diagrams here. This one I'm going to go ahead and draw in one or two maybe particles there. It should not be completely empty. So solids, particles close together, tightly packed. In a, let's say, an ordered crystal structure. They vibrate in place. They retain their own shape. They have a definite shape and volume. They're non-compressible. For liquids, the particles are very tightly packed, but are randomly ordered. They slide past each other. And they have a definite volume, but take the shape of the container. So looking at the way that these particles are packed, basically they're almost the same in the spacing between the particles, and so their densities are almost the same. The liquids for most substances tend to be just a tiny bit farther away in the liquid form, and so the liquid tends to be a tiny bit less dense than solids. That's not the case with water. Water is an exception. But we're going to say slightly lower in density than solids. And I'll say usually because, again, water is an exception. With solids, I'm going to say slightly higher density than liquids. And again, I'll say usually. So if I take some, let's say, melted wax, so it's a liquid, and I drop a piece of solid wax in there, the solid wax will sink to the bottom of my beaker because the solid is slightly more dense than the liquid. That's the normal thing to do. Most substances, the solid is slightly more dense. But with ice, that's an exception. So if I take a cup of liquid water and I put an ice cube in it, it floats. So with water, it's the opposite. The solid is slightly less dense than the liquid. And that's because of the hydrogen bonding, which we'll talk about later. Gases, particles far away from each other. Random, rapid, and constant motion of these particles. Shape and volume of container. Significantly less dense than liquids and solids. And then another main difference between solids, liquids, and gases is the significance of these intermolecular forces. So the big deal here is that these have negligible IMFs. Very strong IMFs, and then strong IMFs. So liquids and solids have pretty strong intermolecular forces. The solids are slightly stronger. With gases, these intermolecular forces are negligible, insignificant. Remember, Chem Ch basically says there's no force of attraction, and so we kind of ignore them. So now that we're talking about solids and liquids, it is a big deal that we discuss these intermolecular forces because they affect a lot of different properties in solids and liquids. So remember that we have intramolecular forces, also known as bonds. And those are the attracting forces within a molecule. So these right here, the actual bonds, those are the intramolecular forces. Then we also have intermolecular forces. So these are the attractive forces between molecules, also known as van der Waals forces. And so if I have a water molecule and another water molecule, that force of attraction between those two molecules is my intermolecular force. So in order to overcome intramolecular forces, in order to overcome this attraction here, the bond, I have to break that bond, which means I need a chemical reaction. In order to overcome intermolecular forces, I just need a physical change, like melting or vaporizing or something like that. And so intramolecular forces, these bonds, are much stronger than the intermolecular forces. And again, to break these, I need a chemical reaction. To break these or overcome these, I need just a physical change. Much easier to vaporize liquid water than it is to break it down into hydrogen and oxygen gases with electrolysis or something like that. So let's look at a variety of different substances and look at what's happening to their electrons, what kind of bonds they have, so intramolecular force, and what type of intermolecular force they have. And just a reminder, this is a continuum. On one extreme, you have ionic substances. On the other extreme, you have nonpolar covalent. So this is ionic, and this is nonpolar covalent. And then in between, you have the polar covalent. So it's a continuum, like we said. So let's look at Br2. So I have two bromine atoms bonded together. They are sharing the electrons equally. So equal sharing of electrons. That's because they have the same electronegativity, obviously, and so they are sharing the electrons equally. We say that this is a nonpolar covalent bond. And, you know, they're attracted to each other. So let's say I have a Br2 here and another Br2 here. There is a slight force of attraction here, not very strong, but those, if you remember, we call those London dispersion forces. And these are the weakest of the IMFs. Okay, let's move on to HI. So with HI, I have my hydrogen bonded to an iodine. Iodine is slightly more electronegative than the hydrogen, and so I get a slight partial negative here, a slight partial positive there, because the electrons are hanging out more with the iodine, so slight unequal sharing. Of those electrons. We call this a moderately polar or slightly polar bond. So covalent though. And if I have an HI here and another HI here, remember, oh sorry, let's make this the H and this the iodine here. So since this is partially negative and this is partially positive, I have an attraction between the positive end of one molecule and the negative end of the other and vice versa. We call these dipole interactions. And they are definitely stronger than these London dispersion forces. Let's look at HCl next. So HCl, I have chlorine is more electronegative than the hydrogen, and so it gets a partial negative, and this gets a partial positive. So the difference in electronegativity here is greater than here. And so, yes, there is still a slight positive and a slight negative, but these partial charges are bigger than these partial charges. So we definitely have unequal sharing for sure here of electrons. We'd say that this bond is definitely a polar bond, polar covalent bond. So that's the intramolecular force. And if I had this HCl and then another HCl, remember that these are a little bit bigger, right? One end of the molecule is attracted to the other end of the molecule because of the partial positive and negative. So stronger dipole interactions here. They're still called dipole interactions, but we're going to say that they're a little bit stronger than these here. Okay, let's move on to HF. So HF, I have hydrogen bonded to fluorine, and there's a huge electronegativity difference here. So this is a really big partial negative. This is a really big partial positive. So definitely very unequal sharing of electrons here. We say that this is a very polar covalent bond. And the interactions here, so if I have an HF and another HF here, with these huge partial positives and negatives, I do have an attraction here. And so these are very, very strong dipole interactions that we don't call them dipole anymore. We call them hydrogen bonding. Hydrogen bonding interactions. And then we have ionic. And so, oops, sorry about that. So we have an Na plus and a Cl minus, right? These are full positives and negatives, not partial anymore, but full positive and negative, which means that I have extreme unequal sharing of electrons, that it's no longer sharing, it is giving and taking away electrons. The sodium gave away its electron to the chlorine. So we have extreme unequal sharing that is giving, or let's say losing and gaining electrons instead. Losing, gaining of electrons. No more really sharing. And we would say that this is an ionic bond, ionic intramolecular force. And if I have another NaCl here, there's a very strong attraction here between the full positive and the full negative. And so we call these ionic interactions. So I want you to look at this as a continuum as opposed to a clear-cut ionic versus polar covalent versus nonpolar covalent. It's a continuum. This is one extreme, and then this is the other extreme, and those are kind of in the middle. Whether it be with the electron sharing, so in this case, it's very equal sharing, slightly unequal, unequal, very unequal, extremely, extremely unequal sharing. So again, it's a continuum. Or whether it's with these partial positives and negatives. So you see like no charges whatsoever, not even partial. Then you get a small partial charge, a little bit bigger partial charge, bigger partial charge, and then extreme large charge that it's a full positive and a full negative here. So again, it's a continuum when it comes to these positive and negative charges. And because of that, the attractions are also a continuum, right? Because all these intermolecular forces are Coulombic attractions. They're attractions between positive and negative. And so here we have the one extreme where they're very, very, very weak. We'll talk about London dispersion in a little bit. But basically, you do get these momentary, instantaneous, tiny little partial positives and negatives that come and go. And so very, very weak attraction. Now you have those partial charges there all the time. Now you have partial charges that are even bigger there all the time. Even bigger partial positives and negatives, and then full positives and negatives. And so the Coulombic attractions increase as you go from nonpolar covalent to slightly polar covalent to polar to very polar to ionic. So again, it's a continuum in terms of all these different things. So as we've mentioned here, this is kind of like a brief overview of the intermolecular forces. We had talked about that in gases, these are insignificant because the particles are so far apart, but in liquids and in solids, those become significant. So the four different types of intermolecular forces that we've listed here are here as well. So ionic forces, these are for ionic substances like NaCl, for example. Dipole forces for polar covalent substances. Hydrogen bonding for very polar covalent substances that contain these. And then London dispersion forces, these are for nonpolar substances. So let's spend a little bit more time talking about these. And before we do that, I want you to take a look at, these boxes that I have here. Remember, if it's in a box, that means it's important. So just a reminder that if you have a physical change, like when you dissolve something, when you melt something, when you vaporize it, you're overcoming these intermolecular forces between the molecules, right? Which is kind of weak, so you need just a physical change. So you overcome these London dispersion forces, dipole forces, and so on. In a chemical change, you are breaking the bonds, the intramolecular, right, the actual bonds. So things like combustion, neutralization, decomposition, actual chemical reactions, the bonds are broken and new bonds are formed. So the ionic or covalent bonds are broken or formed. So that's kind of important to think about. So in a chemical change, you break and form bonds. In a physical change, you overcome intermolecular forces. And I'd like you to use those words. So with intermolecular forces, you want to say overcome intermolecular forces. But with bonds, you want to say broken and formed. Another thing that College Board loves to use is that term Coulombic attraction. Remember, Coulombic attraction means just positive and negative attraction, right? So you want to use Coulombic attractions when you talk about a lot of different things. We talked about Coulombic attractions when it came to Zeph, remember, like, within an atom. Now we're talking about Coulombic attractions when it comes to in between molecules, or the intermolecular forces. So these intermolecular forces are basically just Coulombic attractions. Okay, so let's talk about these four intermolecular forces in a little bit more detail. So the first one is Ionic Interactions. and ionic interactions are the strongest of the intermolecular forces. And from their name, they occur between ionic substances. So if I have one formula unit of NaCl and another formula unit of NaCl here, because I have these full positives and negatives, one ion from one formula unit is attracted to the other ion from another formula unit. The higher that charge that I have here, the stronger these ionic interactions, because obviously they're positive and negative. So if I have something that's +1 and -1 versus +2 and -2, the +2 and the -2 will have stronger ionic interactions than the +1 and -1. So the larger the charge, and the smaller the ion as well, the stronger that interaction. So that's for ionic substances. If we have a covalent substance, then we have three options here: dipole interactions, hydrogen bonding, or London dispersion. Out of these three, hydrogen bonding would be the strongest, followed by dipole interactions, and then London dispersion is the weakest. But stronger than all of these is the ionic, right? So ionic is the strongest, and then these three, and within these three, H bonds are the strongest, followed by dipole, followed by London dispersion. So let's talk more about these three. Dipole interactions, so dipole, two ends or two sides. That means it's going to occur between polar molecules, right? Sided molecules. And what happens is, if you look at this, let's say this is HCl, for example. So if this was HCl, then this would be the H side. This is the chloride side, right? So HCl, HCl, HCl. So if you look, let's look at this chloride or the chlorine side here. Because it is partially negative, it's going to be attracted to all these hydrogens neighboring to it. And so the molecules in a polar substance align themselves so that the positive end of one is attracted to the negative end of the other, and vice versa. So you have all these attractions here, and that's what dipole interactions are. If you have a polar substance, that means it has a dipole moment. And this is not an M, this is actually the Greek letter mu. That sounds like an M, but it's written like a fancy U. And the dipole moment is the extent of the polarity, basically. So it is like a made-up number that we use to tell us how polar or how sided the molecule is, how uneven the distribution of the electron cloud is. So if you have a higher dipole moment, that means your molecule is more polar. Okay, so if I have HI versus HCl, for example, this would have a higher dipole moment. This would have a lower dipole moment because the polarity here is smaller than this one. The sidedness is less here than it is here. Remember, we said this would be like a small partial negative and a small partial positive. Here we'd have a large partial negative and a large partial positive. And so that difference in electronegativity causes a bigger difference in polarity. And so the more polar the molecule, the higher its dipole moment. Okay, so we got dipole interactions. Let's look at hydrogen bonding next. So hydrogen bonding occurs in dipole or in polar molecules as well. It's a special type of dipole. Special type of dipole. It's a stronger type of dipole. So it occurs in molecules that are polar, but only the ones that have an HF, HN, or HO. The reason why it's hydrogen bonded to a fluorine, a nitrogen, or an oxygen is because fluorine, nitrogen, and oxygen are the most electronegative atoms on the periodic table. They also have lone pairs whenever they bond, and so that gives them a little bit more pull. And so when you form your partial positive and your partial negative, they end up being really big partial positives and partial negatives. So those molecules that have these are very polar, not just polar, slightly polar or moderately polar, but very, very polar. So water, for example, here's a water molecule, another water molecule, another water molecule. So it works the same exact way as your dipole interactions. So the one that's more electronegative pulls the electrons towards it. So there's a partial negative here, partial positives there. And the negative end, the partial negative end of one part of your one molecule is attracted to the partial positive end of a neighboring molecule. So this is your hydrogen bonding. It's very poorly named because when you think of hydrogen bond, you think bond, like actual bond. This is not a hydrogen bond. This is right here, those dotted lines. So it's poorly named. Hydrogen bonding, like we said, is a special type of dipole. Because your partial positive and partial negatives are bigger than they normally are in a regular dipole, hydrogen bonding is slightly stronger than a dipole interaction. And hydrogen bonding causes very unique properties of water because of that very, very strong attraction. So water has very high surface tension, has very high capillary action, very high heat of vaporization, very high heat capacity, and very high boiling point. So these are very high because of the hydrogen bonding in water. So surface tension, the reason why water beads up is because of that strong hydrogen bonding. So the water particles are so attracted to each other to create almost a membrane on the outside. Capillary action. This is good because if water did not have very high capillary action, we wouldn't be able to have the plants grow. The way that the plants get their water is through capillary action, through the stems. The water gets to the leaves and the branches and everything through these small stems. So if we didn't have capillary action, very strong capillary action of water, we wouldn't have plants. Heat of vaporization. Water can absorb huge amounts of heat before they vaporize. And so, and large heat capacity, water absorbs lots of heat before it changes its temperature. And that's how we moderate the climate on Earth. The idea that ice is also less dense than water, that has to do with hydrogen bonding as well. And that's how we protect sea life. You know, if ice was more dense, then it would all sink to the bottom and the fish would be frozen in the winter. But what happens is the ice floats and it protects the sea life in the oceans while it's cold. Water has very high boiling point as well. So at 18 grams per mole, you would think that water should have been a gas at room temperature. But because of the strong attractions, the particles are so attracted to each other, condensed together, and it turns out to be a liquid at room temperature, which is very, very unique for water for its size. So all these are because of that very, very strong attraction between the molecules. The last type of intermolecular forces in covalent substances are London dispersion forces. This is named after Fritz London, so a scientist, not the city of London. Dispersion means kind of like movement or spread out of the electrons that we're talking about. So these occur in all molecules. Any molecules with an electron cloud have London dispersion. But they are so weak that they're not really significant in any type of molecules except if they're nonpolar. But again, they occur in all molecules. So something like water also has London dispersion. Something like HCl also has London dispersion. It's just not very strong. And so what happens is, let's say this is Cl2, for example. So you have two neighboring molecules of Cl2. They're nonpolar, their electron clouds are evenly distributed, everything's great. Because the electrons are moving randomly in that electron cloud, let's say just for an instant, by coincidence, randomly, as the electrons are moving, they are concentrated in one area of the molecule more than another. So right here, it looks like the electrons kind of are concentrated in this side of the molecule more than this side. So for that instant, just that little tiny instant, there is a slight partial negative here because there are more electrons, and a slight partial positive here. What that does then, it causes the neighboring molecule to do the same thing. Because this is partially positive now, it's going to attract the electrons that are in this molecule to go this way. And so now the neighboring molecule also has an induced slight, very slight partial negative and a partial positive. And so now that this is partially positive and this is partially negative, there's an attraction right here between those two molecules. It occurs, like I said, just for an instant, and it goes away because it is due to the random motion of the electrons. So just for instant, by coincidence, it can happen, and then it stops as the electrons move away. Then it can happen and then stops. So because it's not a constant partial positive and partial negative, it is extremely weak. The molecules that are a little bit larger with bigger electron clouds, like more electrons, would have a stronger London dispersion than the smaller ones with lower number of electrons. The reason is because if it's larger and has more electrons, you are more likely to have that uneven distribution. When you do, you have more electrons to make it a bigger partial negative and partial positive. So polarization is the extent to which the electron clouds get distorted, the extent of which these electron clouds are not even anymore, just get distorted and become uneven for just a moment by this instantaneous external charge. The higher the number of electrons and the larger the molecule, the higher the polarization and the stronger the intermolecular forces, or the London dispersion. So the key here is the higher the number of electrons. Some students talk about mass. It is not the mass, it is the number of electrons, and the size of the electron cloud is what matters, and the size of the molecule. So if I have like Cl2 versus Br2, this one would have stronger London dispersion than the chlorine because there are more electrons and a bigger molecule. So there's more polarization, higher polarizability. Let's take a look at this graph right here. This actually refers back to the hydrogen bonding. You can see a trend here. This is hydrogen bonded to the oxygen family and to the halogen family here. And you see a trend. And so if you look at this, these are the boiling points, and it looks like HI has a higher boiling point than HBr, than HCl. The reason being is that all of these are polar, but remember, polar molecules also have London dispersion, right? So HI has way more electrons and is bigger, so it has more polarizability, so it has a bigger LD than HBr, than HCl, and so when you combine the dipole interactions and the LDs of HI, they're bigger or stronger than the LDs and the dipoles of HBr. And again, those are bigger than the LDs and the dipole of the HCl. So you see a trend here. And same thing with these here. So based on this trend, you would expect HF to be like way down here, right? But in reality, it's way up there. It has a very high boiling point for its size. Same thing with water. You would expect water to be like somewhere, you know, if you look at this trend, maybe right here, but in reality, water's way up there with a very high boiling point. Reason is because of the hydrogen bonding in these. These experience hydrogen bonding, which are very strong compared to dipole and London dispersion, and so because of that, they have very high boiling points relative to their size. Okay, so remember that all molecules, regardless of their polarity, do have London dispersion. That's kind of a key thing here. So when you look at a substance, how do you know what type of intermolecular forces they have? So the first thing you ask yourself, is it ionic or covalent? And if it's ionic, then it's definitely ionic interactions. If it's covalent, then you ask yourself, is it polar? And if the answer is no, then it only has London dispersion. If the answer is yes, then you check, do you have an HF, HN, or HO in there? And if no, then it has dipole interactions plus London dispersion, of course. If the answer is yes, then it has H bonding plus London dispersion plus dipole as well. It's just that these are weaker than the H bond, so H bond is like the strongest type. Same thing here, dipole is much stronger than LD, and so that's the strongest type. So let's look at this here. It says list all the intermolecular forces in each of the following and place them in order of increasing intermolecular force strength. So let's look at chlorine. So ask yourself, is it ionic or covalent? It is covalent. So then you ask yourself, is it polar? The answer is no, so it only has London dispersion. Okay, CH3CN. So this looks like this. So you ask yourself, is it ionic or covalent? It's covalent. Is it polar? Yes. Does it have HF, HN, or HO? No. So it has dipole and London dispersion. C3H7OH. So that looks like a bunch of carbons with an OH. And there are hydrogens here. Is it ionic or covalent? It is covalent. Is it polar? Yes, it is. Does it have HF, HN, or HO? Yes, it does. And so it has H bonding. And also dipole and also London dispersion. KOH, ionic or covalent? That is ionic. So it has ionic interactions. Next one, C2H6, looks like this. So you ask yourself, is it ionic or covalent? It's covalent. Is it polar? No, so it just has London dispersion. CH3CP looks exactly the same as this one, except there's a phosphorus instead of a nitrogen. And so let's go ahead and draw it, just so we have it. And so this one is, you ask yourself, ionic or covalent? It's covalent. Is it polar? Yes. Does it have HF, HN, or HO? No. So it has dipole and LD. Okay, so we figured out what type of intermolecular forces it has. And then next we want to place them in order of increasing intermolecular forces. So weakest to strongest. So the weakest out of all these would be the ones that are just LD. So which one is even weaker? So what you look at is the number of electrons and the size. And so there are way less electrons here than there. And so this is the weakest, followed by, this is number 2. Next would be the ones that have dipole interactions. And so those two. And so between those two, you would say, since we have a dipole interaction here, you want to look at your dipole moment. There's a bigger partial positive and negative here than there is here because the electronegativity difference between those two is stronger. And so I'd say this would be number 3 and this would be number 4. Next, you want to do the one with H bonding, so that would be number 5. And then the ionic interactions would be the strongest out of all of them.